All right, we are moving on with our lectures in signal processing, and what we're going to start covering now is a series of lectures on the Fourier transform. So we've already been working around the concept of Fourier series and representation of signals in terms of Fourier series, but now we're going to go right into what's called the Fourier transform and one of the workhorse algorithms of computational science, which is the fast Fourier transform, which allows us very easily to move into the Fourier domain and back out of the Fourier domain. And this is probably one of the most important transforms you'll ever learn because we use it across the board in almost all applications where we need to start thinking about, well, certainly for signal processing applications, but more broadly in science and engineering, the Fourier transform shows up everywhere. It gives us an alternative representation of much of our signal and allows us to do a lot of sophisticated processing and work for getting solutions of different types of problems. So we'll also highlight the difference between the Fourier transform and just the Fourier series representation, because really at the end of the day, all the Fourier transform is going to be a representation in terms of Fourier series. Okay, so first of all, let's define the Fourier transform, and here is the definition of the Fourier transform. It is a pair. It is x of t here, so this is my signal. I can represent my x of t as a transform 1 over 2 pi, negative infinity, infinity, x of I omega, e to the I omega t d omega. So here I'm integrating over all frequencies times x of I omega, which is the representation of the signal in the Fourier domain. When we were looking at Fourier series, this x of I omega was really our a of k's. In other words, the coefficient of each of the Fourier modes. But notice the difference here. We've replaced the sum of Fourier modes by not a sum, by an integral. In other words, it's continuously integrating over all frequencies. So this x of I omega is not just specific a of k's. It is a continuous function of all omegas, right, that I integrate over. The way you get these x of I omegas is very much like what we did in the Fourier series representation. You actually compute the signal projected onto each of the Fourier modes, but now again it's a continuum. So x of I omega is given here. Okay, so x of I omega is here, where now I integrate the signal x of t against e to the minus I omega t dt and integrate from negative infinity to infinity. So a few things to note then. We've moved from sums to integrals. That's one. And two, to go into the Fourier domain, I take my signal and I multiply by e to the minus omega t and integrate over all time. And to come back out, I multiply by e to the plus I omega t, and then I integrate over all frequencies. So this Fourier transform pair is going to be critically important for us, and what we want are algorithms, of course, that are going to approximate this. And in many cases, you can actually explicitly work out these integrals. And when we do work out these integrals explicitly, we put them in Fourier transform tables, which we will cover a little bit later in our lectures. Okay, so those are the Fourier transform pairs. And let's talk about some practicalities first, which is first defining things over all time and over all frequencies. In other words, this idea of going from negative infinity to infinity. So, but before we do that, let's, here we go. Okay, let's talk about here another representation of this, which is one representation of this is this little script f, which is x of t goes into x of I omega. So now I'm in the time domain, and this Fourier transform puts me now in the frequency domain. And that's sort of this canonical representation of frequency coordinates, time coordinates. And I can go back from frequency to time by the inverse transform. So this representation is a sort of a shorthand way, and what it really is telling you is what you're doing in Fourier transforms, and we've highlighted this earlier, is you are making a coordinate transformation into an infinite dimensional orthogonal space of modes that you're going to be working with. So this coordinate system is quite nice and advantageous for you. And so what we want to start thinking about is how do I move back and forth between these in some effective way, right? And so I go from x to omega, and then I want to do all my manipulations in this new space that I'm working in. Okay, so let's talk some practicalities. So in practice, If you notice what I did here, we defined this on some interval, negative infinity to infinity, but of course in practice, nothing goes to infinity. We're going to do some computations, so we're going to have finite size domain. So really, we could think about this as that is an approximation to some finite domain, negative t to t, where we take t to be large. But really, there's even one more approximation that happens in the fast Fourier transform, which is we're going to be working on the interval always of 0 to 2 pi. So we're going to take some time signal, and we're going to think about always scaling it down to 0 to 2 pi, which is going to be our fundamental domain that we're going to work in on with the fast Fourier transform. So those are some practicalities just to keep in mind, right, as we do this. So we're going to take any signal, we're going to think about whatever time bin we're looking at as being sort of negative infinity to infinity, and then rescaling that to 0 to 2 pi. Okay? So when you do the FFT, the fast Fourier transform, in Python or in MATLAB, it always believes you're on a 2 pi periodic domain. So we're going to make all of our time bins fit into that through scaling. Okay, so that's a real practicality that we have in practice. But for a while, what we're going to do is just consider this all in theory. So for now, let's go ahead and back and work with this infinite dimensional representation here, which is we're going to integrate over all of time and from negative infinity to infinity. Okay, so first of all, we have to have some convergence criteria, and in fact, it's very much like what we had with a Fourier series representation. First, you actually have to have this condition hold here, which is actually supposed to be the absolute value squared. dt has to be, has to actually be finite value. Okay, so this is the first condition that you would have to hold in order for the signal to be represented by a Fourier transform. Okay, so you can't have some infinite signals in there. Second and third criteria is that first there has to be a finite number of maximum and minimum for that signal x of t, and there's a finite number of discontinuities. So you can have discontinuities in your signal, and the Fourier transform will handle them, but it has to be a finite number. And also you can't have, what this means, number two here, finite number of maximum, and you can't have something that oscillates an infinite number of times in some time bin that you're looking at to Fourier transform. So those are the restrictions on where the Fourier transform holds, but of course, 2 and 3 typically for any reasonable signal are always going to hold, and typically you're not looking at signals that are going to infinity anyway. So these are all pretty practical and simple considerations, and that basically suggests that for the most part, the Fourier transform is always going to work for you, except for these weird exceptional cases, which are more mathematical exceptions than they are in practice any kind of exception. So let's do an example where we work out the Fourier transform directly in theory of a given signal. And here's a signal that we might want to consider. X of t is equal to, this is some decay, exponential decay, e to minus at, and it turns on at time 0. So, so it's 0, and then we get this spike, and then it decays down. So that's what this means, and we're going to take a as positive. So all we have to do is throw this directly in to our Fourier transform. And here it is. So we throw it in and say, what's the Fourier transform of this? Well, just put your signal in there into the integrand, x of t, but now notice it's e to minus a of t, u of t, but the u of t is 0 everywhere until time 0, then it's 1. So this integral negative infinity to infinity is actually going to go from 0 to infinity, and now I just integrate over these two exponentials. And exponentials is trivial to integrate, right? One of the simplest things we did or learned early on in calculus was how to integrate an exponential. And so what you find is when you integrate that exponential, this is the output here, which is what you're finding here is the frequency components are 1 over a plus I omega. Okay, that is the Fourier transform of this function here. So the nice thing is if you ever see this function again, then you just can say, here's what it looks like in the Fourier domain. It has a very specific representation in the Fourier domain. In fact, you can kind of plot out what this might look like. And here up top, this is what it looks like in the Fourier domain. If I plot this, is the absolute value of this function. And this, of course, becomes very important for us to think about, which is what does the function that I'm Fourier transform look like in the Fourier domain? That's what that signal looks like. And you can even represent its phase. So the phase is, basically the phase of a signal is the phase between the real and imaginary parts of the signal, and this is what it looks like across that signal. So if we come back here and say, okay, for this specific Fourier transform, when I look at this function here in Fourier domain, I can look at its absolute value as well as its phase. And those two completely characterize what's going to happen to that signal in the Fourier domain, how to represent it in the Fourier domain. And remember, what we're going to do is we're going to manipulate signals in the Fourier domain. So this is the big deal that we have with Fourier transforms, is we're going to move into the Fourier domain, we're going to do the manipulations in the Fourier domain, and then come back into our time domain. And so understanding what the signals look like in the Fourier domain becomes critical for us if we're going to actually start doing manipulations. Okay, here's a second example. So really this is just all integral calculus, and in fact there's a bunch of standard example functions that you can run through a Fourier transform that give you some very nice results in the output. And like I said, we've put these into a Fourier transform table and sort of basically a lookup table. So you have a bunch of functions that have already been pre-computed of what they look like in the Fourier domain, and so you can just look that up in the table and see what that looks like. But this is how you would derive these things, right? So if we look here at this function here, which is a exponentially decaying function with a absolute value of t, so in other words, it looks like a little bit like a tent function, a smooth tent, then you can just put that through the integral. It's pretty easy to integrate this thing, and this is your result. This is the function in time, and this is the representation of that function in the Fourier domain. Okay, so again, we can plot this. Here was what the function looks like in time. Here's what it looks like in the Fourier domain. And again, this is like the tent function I just showed you, right? It has a sharp cusp here. It's the absolute value of the exponent, so it decays on both sides. And then this is what it looks like in the Fourier domain. So again, you have these what are called Fourier transform pairs. You have a function in the time domain. It has a corresponding piece in the frequency domain. And we're going to move back and forth between these sort of in our most convenient way so that we can make use of this information to do signal processing. Let me give you one other very important example, and this is an on switch. So x of t, right, if you look at this thing here, it's 1 when t is in some between negative t1 and t1, and it's 0 otherwise. So this is just a simple on switch, and then you ask the question, what does an on switch look like in the Fourier domain? Well, you can actually just simply integrate that. So you throw that into the integral. The integral is trivial to do, and what you end up with is a sinc function, a sine x over x type behavior, and this is what it looks like here. So if you take a Fourier transform of a on switch, this is what it looks like in the Fourier domain. Okay, you get this slow decay like 1 over x as you drop out to higher frequencies. Okay, and in fact, this is partly why you don't want to filter with sharp cutoff filters like this, because I'm going to show you that if you filter in the frequency domain with something like this, you get this kind of behavior in time, which means the filter itself produces all these oscillations that decay very slowly away from where you want the signal. So using these square chops in the frequency domain are highly advantageous in many ways because of this, what you're seeing right here, which is it produces this long scale effect which decays very slowly, this ringing, as it were, in the field. So these are all sort of 3 examples of functions that we would Fourier transform. And again, many of our simple functions that we work with, sines, cosines, exponents, Gaussians, the on switches, the delta functions, they all have very simple representations in the Fourier domain. And so a Fourier transform table has all this information, and it tells us how we move from the time domain into the frequency domain. And remember, the entire objective here is, once we get in that frequency domain, is to figure out how to leverage that information in the frequency domain to do signal processing. And these are very nice representations of the signal that we can now take advantage of and do filtering operations or manipulations in order for us to shape what we want as the output to our, for instance, LTI system. So more on the Fourier transform. And again, the Fourier transform, we execute this Fourier transform in practice with the fast Fourier transform, which is one of the most important algorithms for signal processing that we will encounter in general over all of science and engineering.